Hi everybody, Cal here with sections 4.5 and 4.6. 4.5 is called the dimension of a vector space, and you may have noticed that I've been assiduously avoiding the term dimension for the entire course, and that's because we couldn't precisely define it until now. We're going to start the section with a couple of theorems that will let us define dimension. Theorem 9 says that if I have a vector space with a basis consisting of a certain number of vectors, then any set with more than that many vectors can't be linearly independent. The proof of it is pretty simple. It just uses coordinates, and it's worth reading through and puzzling through. This is a proof you could certainly do yourself at this point. Going on to the next page, if you apply Theorem 9 twice in a certain way, you'll get Theorem 10. Once I know that a vector space has a basis of n vectors, every basis of that vector space must have exactly n vectors. Again, the proof is worth going through. It's pretty simple. What this means is that the number of vectors in a basis for a given vector space is well defined, and that's what we're going to take to be the dimension of a vector space. So the definition here is that if a vector space is spanned by a finite set, there are a finite number of vectors in any basis for it, and that number is well defined. We'll take that number as the dimension of our vector space. Some vector spaces are not finite dimensional, they're infinite dimensional. They cannot be spanned by a finite number of vectors. We're going to be concerning ourselves mostly with finite dimensional spaces. So, the first few examples kind of let us get at the dimension of some well-known spaces. I would go through all these examples. They're worth your time. Theorem 11 tells us a little something about what subspaces of a finite dimensional space can look like in terms of dimension. And Theorem 12 is a big one. It's called the basis theorem. You know that if it's a named theorem, it's probably worth knowing, and this one is no exception. The basis theorem basically says that once I know the dimension of a space, if I have a set of that many vectors in my space, if it is linearly independent, it's a basis. It automatically spans. If it spans, then it's linearly independent. So knowing one of the two properties of a basis in this case gives me both, if I have a set of p vectors in a p-dimensional vector space. That's pretty big news. Then we have a discussion of what are the dimensions of the null space and column space of a matrix. You should think of these in terms of pivots in A. And that's really about all there is to say about this section. It's a pretty profound concept, but not a hard one. Example 5, of course, is just looking at dimensions of the null and column space of a given matrix. Moving on to section 4.6, rank. We're going to start by introducing the third and final big subspace of a matrix called the row space of that matrix. If the column space of a matrix is the span of the columns of that matrix, well, the row space of a matrix is the span of the rows of that matrix. Not terribly hard. You might have a hint in your head that you could maybe get at things by using transposes here, since transposing turns rows into columns, and you would be correct. If you read this carefully, you'll see what's going on. Read through example 1, and I would read Theorem 13, which kind of gives us a recipe for finding a basis for a row space. So read that one carefully. Example 2 will let us apply that to an example. And that's worth your time. We will be looking for bases of row spaces, so to speak. In fact, I would say example 2 is very common. You can pretty much expect to see something like this on any of your exams from here on out. Okay, so definition on this page. The rank of a matrix is just a short word for the dimension of the column space of that matrix. The dimension of the null space is sometimes called the nullity. of the matrix. We're not going to use it a heck of a lot. At any rate, the big theorem here is Theorem 14, the rank theorem. Think about what this theorem says in terms of pivots of A. And if you, well, it says it right down here, but if you understand what's going on there, then this theorem should not seem like a shock. Example 3 is valuable. Kind of lets us think a little bit about using rank, using these dimensions to make conclusions about matrices. Example 4 is more of the same. And example 5 is actually a lot of fun. I would give this a careful read. You do have one like this on the homework. I have occasionally asked questions like this on tests. So example 5 is worth your time. At this point, your book kind of expands the invertible matrix theorem. We've had that sitting in our back pocket for a while now, and we have a whole bunch more things that we've introduced in this chapter that are still equivalent to a matrix being invertible. So this is a generalization of Theorem 8 from Chapter 2, the invertible matrix theorem. And this is, again, not something to memorize, but something to understand. And that's about it for this section.